Okay. All right, guys. Welcome back to another week's of interactive session of the course Viscous Fluid Flow. And we are in week 8, and gradually we are moving towards the fag end of the course. And I hope you are, I know, I mean, you guys are doing well with your assignments and regularly watching the week's contents as well of the course. So we'll begin from where we left. So if you remember, in in the last uh, week, we looked into a special class of flows, which we call it as creeping flows. And then we argued that we kind of non-dimensionalize the full Navier-Stokes equation. And then we said that in the limit when Reynolds number basically goes to zero, the Navier-Stokes equation, which are inherently nonlinear, especially because of the term u dot grad u, in the limit when Reynolds number goes to zero, leads to a linear system of linear, I would say it leads to a linear equation, uh, which are basically the creeping flow equations which we saw. So it just says that the inertia term that just drops out, and then we get a equation which establishes a balance between the pressure gradient and the viscous forces, which is inherently the hallmark of creeping flows of creeping flows basically. And also we have the as usual continuity equation which always follows the creeping flow equations. So we looked into an important consequence of this linearity of creeping flows is that uh, so we looked into some consequences which be which could be argued based on because of the fact that the creeping flow equations are linear. And one such examples was that in the limit of creeping flow analysis, the drags on objects which are mirror images to one another, they are exactly the same, which is not the case. And intuitively, if inertia is present, this is always not the case, because of the fact that, for instance, this object appears to be a bluff body in the direction of flow with respect to its mirror image. But we argued that in the creeping flow limit, this increase or decrease in drag force with respect to one another is essentially a consequence of inertia. This is something that we argued. And when inertia is not present, we said that the drag forces are exactly going to be equal. And we argued that once again based on the linearity of the creeping flow analysis. Okay. uh, and then we also looked into a different example, and we asked a question that, okay, if I now have a sphere which is rotating with a known or unknown angular velocity omega, and if it is subjected to a shear flow which is off centered to the center of rotation of the particle, and in that case, will the particle, if it is undergoing a rotation with some angular velocity omega, will the sphere or will the particle or will the spherical particle experience a lift force? And then we again use the consequence of linearity of the equations. And as we said, that since the governing equations are linear, the complex problem, so this total problem can be decomposed into three simpler problems. And we argued that since the individual lift forces of the three simpler decomposed problems were basically equal to zero, meaning that since the governing equations were linear, the lift for the for the total problem, I would say, is basically equals to zero. And again, that is an essential consequence of the linearity of the creeping flow equations. And a similar case is say that is something that we saw. We didn't explicitly discuss this, but intuitively we saw that the similar analogy can be drawn for a particle that is subjected to a possible flow. And we said that this particle would not suffer any lateral migration, or it would not suffer any lift force, because of the fact that once again the creeping flow equations are linear. And the problem is kind of, we stated a term, we call it as 4f symmetric. And since the problem is 4f symmetric, the lift force is basically equal to zero, or the particle won't suffer any lateral migration. However, there are work which shows that even if there is slightest of inertia that is present in this scenario, the particle would basically either move towards the wall or move towards the center line, depending on actually where the particle is. And there are very nice papers on this. You can look into these papers. So you can search papers like lateral migration of sphere in a weakly inertial, parabolic flow, and then you will appreciate that if there is some inertia that is present in the problem, then of course the particle will suffer lateral migration. But if there is no inertia, or if we're in the creeping flow regimes, then the particle won't suffer a lateral migration when subjected to a parabolic flow of this form. Okay. Of course, this is again uh, argued by the linearity of the creeping flow equations. And then we ended our discussion by having a small brief, recap, I would say, of the spherical coordinate system, because as I said that today we'll be solving a problem involving creeping flow, and I'll discuss the problem very shortly. But for that, we will require the spherical coordinate system. And then in the last class, we saw the relationship between the Cartesian and the spherical coordinate system. And overall, we got a gist of how the spherical coordinate system works. For instance, the spherical coordinate system is denoted by the orthogonal vectors r, theta, and phi. Okay. And this is how the spherical coordinate system works. And we saw the corresponding Cartesian system and the corresponding cylindrical system rho, z, and phi, and how these three systems are interlinked with one another, basically. Okay. But in today's discussion, we will be solving a problem involving creeping flow analysis. And there we'll be using the spherical coordinate system, and that's the idea why we basically had a gist on how the spherical coordinate system essentially works. Okay. With this, let's begin with today's contents. So today, uh, we will basically see an approach to solve the creeping flow equations, and we'll be sticking to we'll be involved in a domain either which is either 2D or it is axisymmetric. Okay. And then because of the fact that my domain is 2D or axisymmetric, we'll be using an approach which is known as the stream function approach. And you have seen this when we were basically deriving the Stokes drag for a sphere that is subjected to an unbounded, unidirectional flow. And you saw that you saw basically that the drag force comes out to be 6 pi mu u times LC. That's the drag force that basically you get. And when you solve that, you saw that the problem was inherently planar. In fact, that problem was inherently axisymmetric. Okay. So for planar or axisymmetric problems, there is a means of solving the creeping flow equations, and that means is by the stream function approach. And we will solve a similar problem, but a more involved problem rather than the Stokes drags problem. And then we'll appreciate that, okay, how, so it will give us a flavor of and it will give us an idea so as to how to work with these creeping flow equations by using the stream function approach. Okay. That's the idea. And that problem that I was saying is nothing but the motion of a sphere in an unbounded background parabolic flow. So remember, uh, the problem that you solved in the lecture series was that of a sphere that was subjected to a unidirectional, uniform flow. And you said that the question that you asked, that's what would be the drag force that the sphere would experience. That's the question that you asked. We will be solving a similar problem. That is, now instead of calculating the drag force, what we will say is that, okay, now if my sphere, if it is subjected to a unbounded parabolic flow, which is a one step enhancement, I would say, of a unidirectional flow. I would say it's a two-step enhancement, because the one step enhancement would be a shear flow. But now instead of taking a shear flow, we'll consider a more general case, that is a more realistic case of background flows, which are essentially parabolic flows, because these are the flows that takes place in pipes actually. Okay. And we'll consider a background parabolic flow, and we'll now try to understand that, okay, now if I place a sphere in a background parabolic flow, and I say that the sphere is now moving with a constant velocity u, which is unknown and which we'll find as a part of our problem, then what would be the flow field in that case, and what is that unknown velocity of the sphere? Now this is something that we'll try to understand, and then we'll be using something which is known as a force, which is basically known as a hydrodynamic force free condition. This is actually a result of the fact that since the sphere is now moving with a constant velocity u, this means that there always has to be a balance of force that comes from the Newton's second law, right? So now what are the forces that can get balanced? So one force is that there is an external force that the sphere experiences because of the fact that there is a parabolic flow, due to which the sphere will basically experience that external force. And that external force, if it gets balanced by the drag force, then because of the balance of these two forces, the sphere would move with a constant velocity u. So that balance, we will use it to basically find out the unknown velocity u. So that's an extra equation that we will use to basically capture what will be the yet unknown uniform velocity of the sphere when it is subjected to an unbounded parabolic flow. So I hope you got the idea what we are basically supposed to do in this exercise. Okay, and yes, we are in the creeping flow limits, and we will see that this problem is essentially an axisymmetric problem. So we'll be using, the stream function approach, that is will basically solve, as you saw, the biharmonic equation that the stream function satisfies, to basically come out with what would be, the flow field and the unknown velocity of the sphere by imposing the hydrodynamic force free condition. Okay, so before, just starting the solution of the second part, that is the motion of a sphere in an unbounded background flow, I would quickly summarize so as to how we essentially get the biharmonic equation for the stream function from, the Stokes flow equation or the creeping flow equations. So if you remember the creeping flow equations that we saw in the last class, and we also had a recap, was that like it was gradient of P plus, del square V equals to 0, where, I think we wrote u or v, whatever used, that's the velocity field that we are referring to. And okay, we'll write it as u because we had been using the notation u. So better, let's just stick to one notation. So it was minus gradient of p plus the Laplacian of the velocity field is equal to 0, and also we have the continuity equation, which is divergence of u equal to 0. Okay, now in order to get the equation that the stream function satisfies, what we basically do is, I mean, you have done this, I mean, you have seen this in the theory classes. So this is just a recapitulation of what you did. So I hope you are aware of what I am doing right now. So what we do is we basically take a curl. So we take a curl of this. So taking a curl of, let's say this equation is what? Let's say A. Okay, so we'll take a curl of equation A of equation A on both sides, and since the right hand side is 0, it just ends up being 0. So it just happens to be that curl of gradient of P plus curl of del square U, this is 0. And there is a very famous vector identity that if I have a scalar function, if A is a scalar function, if A is a scalar function, then then the curl of grad A is basically 0, which means since my pressure is just a scalar function, this term is basically 0. So I just end up getting, I just end up getting curl of del square U, this is 0, this is basically equals to 0. And then what I'll do is I'll just interchange this del square and the curl operator. Okay, that you can do because of the fact that your u is kind of a continuous function, so you can do that. So this now becomes del square curl of u, and this is 0. Okay, now we know that we define something which is known as the vorticity, which we denote it as omega. This is also a vector. So if my omega is vorticity, then remember the relationship between the vorticity and the velocity field is that my curl of the velocity field basically gives me vorticity. Okay, which means I can just write that del square of my vorticity is basically equals to 0. Okay, I hope you are with me on this so far. And now just let this equation be some equation. Let's say, okay, let's not name it as 1. Let's name it as b, because in the next problem we'll be naming equations in 1, 1, 2, and 3, and so on and so forth. Okay, all right. So now, as you can see that in the creeping flow limit, okay, just by taking a curl of the of the creeping flow equations, you get to see that your vorticity basically satisfies the Laplace equation. That is, your del square of vorticity is equals to 0. Okay, now see, the idea was to find out an equation for stream function. Remember, that's what we need to do. Okay, so now what we'll do is, if let's say I have a velocity field v, then I think you guys know about this, that I can always define a stream function vector, which is nothing but my curl of. So I can always define a stream function vector, let's say psi bar, which if you take a curl, you basically gets the velocity field. That's the definition, okay, of stream function, which means that Okay, so if you remember this psi bar, this is nothing but the stream function vector. And in true sense, even if we just naively say that stream function is used for 2D or axisymmetric flows, and we just define it as psi. But in true sense, stream function is essentially a vector, and what we use is basically, if for 2D or planar flows, we basically take the magnitude of that stream function vector, which is psi, and that magnitude is essentially known as stream function because its direction is always fixed if we are considering a 2D or an axisymmetric flow, and that's the stream function we essentially consider. But in true sense, stream function is essentially a vector. That again is because of the fact that it is related to the velocity by a curl. So curl of anything gives you, so curl of a vector is only, so it's like this velocity can become a vector if you just take curl of another vector, which is the stream function vector. Okay, all right. So this is known as the stream function vector. Okay, now what I was saying is that in for planar or axisymmetric flows, okay, what you can do is you can define, or you can rewrite the stream function vector psi bar as psi times, let's say, Ez, if we are solving for the flow field in the xy coordinate. This means I can then rewrite this relationship between velocity and stream function as curl of psi Ez. Okay, that means you are just taking a curl on the psi Ez, and then you can appreciate that since I am taking a curl with a vector which is just a component in the Ez direction, this means that my velocity field is bound to be having components in the ex and ey direction, and then hence it makes sense that you can then use this psi, which we call it as the stream function for planar and axisymmetric flows. I hope you understand what I'm trying to say here. Okay, I repeat that in case of planar and axisymmetric flows, what you can do is you can define the stream function vector as its magnitude times the direction, which is basically the unit vector normal to the plane on which you are looking for the velocity field. Okay, and then the stream function is so defined that it just gives you that if you take the curl of this stream function vector, you will essentially see that since the stream function vector is pointed in a direction normal to the I mean, so its direction is basically normal to the xy plane. Let's say for this instance, the velocity field, since you are taking a curl, is bound to be in the xy plane. That is, the velocity field in short will just have this ex and ey component. And then in this sense, if you define this, and then in this sense, if you call this psi, if you look into this psi, then this psi is known as your stream function. Okay, and then and this is essentially the stream function that we work on, and then this is the case where we say that okay, stream function is used for 2D or axisymmetric flows. And I hope you now understand that you now understand the big picture behind saying that okay, when I say psi, it's basically actually it is the magnitude of the stream function vector, and the direction of the stream function vector is the direction which is normal to the plane on which we are looking for the velocity field. Okay, that's the idea. All right, but that's not done yet. We are I hope you kind of realize that what essentially and why do we basically say that okay, stream function is used when we have a 2D or an axisymmetric problem. So this is the idea behind this. Okay, but anyways, so what we will now do is, so we are still left to find out an equation for the stream function. Okay, and then what we will do is we'll do the following. Okay, uh, so so what we will do is, so what we got is we basically got an equation for vorticity, right? Now, since we already said that we are in a planar or an axisymmetric problem, so for an axisymmetric or 2D problem, okay, and say for simplicity, say I am just writing it in the xy plane. Just you can write it in any plane. It's just a matter of simplicity and a matter of convenience that I am showing here. Okay. So let's say we are now in the xy plane. That means that the direction of the stream function vector is in the Ez direction. I hope you realize what I am saying here. And then what I can do is, for this case, for an x for a 2D problem, let's say we are in the xy plane. This similar analogy holds good for an axisymmetric problem as well. I can say that my vorticity, okay, this vorticity is what? So this vorticity is nothing but del v by del x minus del u by del y ez. Okay, this essentially is the direction of for vorticity if we are in the xy plane. I hope you realized, because the vorticity will always face in the direction normal to the xy plane. Okay, which means that my magnitude of vorticity is nothing but del v by del x minus del u by del y. Okay, now since I know that my stream function psi, I hope you, so by now at least you know that said, okay, since I know that my curl of the stream function is basically the velocity field, so I can always say that my u is nothing but del v by del y. Okay, or sorry, u, so, okay, I wrote, that's a mistake. Okay, so u is nothing but, okay, did I make a mistake here? Oh, sorry. Yeah, so what I was trying to say is that I can always write u now. So if I have a stream function, I can always write u as del psi, or it's the other way around that I was trying to say. So I can always write my stream function psi as what? I can write it as, okay, is this the better way? Just let me think. What's the, okay, so let's start from the scratch. Okay, so what do I know? I know that my, my uh, my velocity field is nothing but my curl of the stream function. Okay, that's that's how we define. This means that if I take a curl, so what this would be? So this would be ex, ey, and ez. Okay, it's just that we are trying to relate the velocity field with the stream function. That's all that we are trying to do. Okay, and then I have this curl, so which is del del x, del del y, and del del z. And for the planar problem that I have considered, my psi bar is nothing but psi ez. That's the direction of stream function. Okay, so this is 0, 0, and psi. Okay, which means that the relationship between velocity and stream function is that it just becomes del psi by del y ex minus del psi by del x ey. Okay, and then also I can write my velocity field as u ex, which is the, which is the which is the x direction velocity, plus v ey. And then if I just compare these two terms, my u becomes del psi by del y, and my v becomes minus del psi by del x. Okay, so that's what I was trying to say. So u, which is the velocity component in the x direction, becomes, del psi by del y, and v becomes minus del psi by del x. Okay, all right. So I was just confusing. So when I was just writing, I was just confusing with whether this becomes minus or this becomes plus, and that's why it's always better to derive it from the scratch, and that's what we basically saw. Okay, all right. So this is how the stream functions are related with the velocity field in in case of a planar flow. And for instance, we are just considering it in the xy plane. You can consider it in any plane of interest, but just keep in mind that it has to be a planar or it has to be an axisymmetric problem. Okay, all right. So then if I substitute this, if I basically substitute this here, then I can relate the vorticity and stream function as omega equal to del del x of v is nothing but minus of del psi by del x minus del del y of u, which is nothing but del psi by del y. So what we are doing is we are just, using this equation into this equation. That's the thing that we are doing. Okay, all right. I hope like you are with me on this so far. Okay, and then what do we get? That means what we get is omega is nothing but minus of del square psi by del x square plus del square psi by del y square. Okay, which means what we get is that the vorticity, remember this is the magnitude of vorticity, the direction is in the same direction to that of the stream function vector, that is the Ez direction, but its magnitude is nothing but minus Laplacian of the stream function. So this is once again a very important result for for planar flows. Okay, that is your vorticity is always negative of the Laplacian of the stream function. Okay, now if I just name this as equation basically, let's say B or C, maybe this would be C. So if I just substitute this equation C into this equation B, which just says that del square of omega is equal to 0, then I can just write it as, okay, then I can just write this. So equation B gives me what? It just gives me that del square of omega is equals to 0. But since since we are in a planar flow, I know that my omega bar is just omega times Ez, which means if I write an equation for for omega, then it just becomes that del square of omega is equal to 0 for for a planar flow basically. Okay, and then if I use the fact that, and then from C, since my omega is nothing but minus del square of psi, then I can write this as del square of I hope you are with me on this so far. It's just substitution that I'm just doing. It just becomes del square of minus del square of psi is equals to 0, and this just becomes del square of del square psi is equals to 0, and then it just ends up being del 4 psi as 0. Okay, so that's the equation that the stream function satisfies. uh, for I'll again write this for a planar or an axisymmetric flow. Okay, that is the stream function. That is, so you can basically argue that the stream function psi satisfies the biharmonic equation. Okay, I hope you are with me on this so far. Where we know that where this del square is nothing but like for like in the xy plane, this del square becomes del 2 by del x2 plus del 2 by del y2, which is nothing but the Laplacian operator. Okay, and you just take a square of this Laplacian operator basically to get the biharmonic operator, which is del 4 psi. Okay, now the idea is that since we'll be dealing in spherical coordinate, I hope you understood, and this is just a recap of what you basically looked into in the theory classes. The idea now is that since we'll be using spherical coordinate system, the stream function in so I'll write it down that in spherical space, okay, the equation that the stream function satisfies is again the biharmonic biharmonic equation, but it is written as E4 psi equals to 0, where where, so just to distinguish between a Cartesian space and a spherical space, in case of del we use E, where E square in the spherical space is defined as del 2 by del r2 plus 1 minus eta square by r square del 2 by del eta 2. Okay, where this eta is basically equal to the cos theta, and then this is the equation, this is the biharmonic equation that the stream function satisfies in spherical space, and this is for the case of an axisymmetric problem. Okay, this is for the case for an axisymmetric problem in spherical coordinate system. Remember that when we are considering axisymmetry in spherical coordinate system, this means that my variables are just a function of the r and a function of theta. It is not a function of phi. That means that if I move around the z axis, basically my variable just remains the same because it is phi independent, and that is the definition of axisymmetry in spherical coordinate system. And as I said, that stream functions can also be used for axisymmetric problem. This means that the same stream function. So it just means that the stream function vector, this will basically have a direction. This will have a magnitude and it will have a direction in the e phi direction. It will always point in the plane, that is, it is always point orthogonal to the plane of the interest that we are basically looking into. Now, since we are in the r theta plane, its direction will be along phi. That's the idea. That is the direction of the stream function vector. Okay. For instance, if you want to look into the relationship between velocity and stream function in spherical space, the velocity is nothing but it is just curl of the stream function vector psi. That's the basic definition, and this is related as curl of the stream function psi by r times square root of 1 minus eta square e5. That this is how the velocity is related to the stream function in spherical space, in case of problems having spherical axisymmetry. Okay, that is the stream function vector is oriented in the direction of e5 direction, in the direction of e5 basically. That is in the azimuthal direction. All right. So that's the background. That's the background that we will need to basically solve this problem. And I'll just stop here for a couple of minutes, and then we'll begin. We'll just tackle the problem head on now. That we'll just basically go ahead and solve the problem. That sphere that is moving with an unknown velocity u, which we'll be finding as a part of our solution when it is subjected to a background parabolic flow. Okay. And just for the sake of simplicity, as I have said, uh, the problem is essentially spherically axisymmetric, which means that we will use the stream function, and what we will do is we'll just look into the solution of this e4 psi equal to 0. And trust me, we'll just not solve this, but we will be using this solution to basically get get the unknowns of the constants of the form of the solution that we will see very shortly, to basically solve the problem and get the unknown velocity u that we are looking to solve for. Okay, that's the idea. We'll be dealing this very systematically, but that's the idea that we will follow. Okay, I'll stop here for a couple of minutes, just for you to digest whatever we did so far, and then we'll begin by solving the problem. And just for you, this is the problem that we'll basically solve. Okay, and I'll just write. Oops. Okay. I will just write, one line here in the drifting flow limit. Okay, so as I said, this is the problem that we'll basically solve, and we'll be solving this very systematically and in a step-by-step manner. Just that you get a feel of whatever the things that we are actually kind of doing here. But before that, let me once again formally state the problem. So I have a sphere, okay, of some, let's say, known radius a being the radius of the sphere, and this sphere is subjected to a background parabolic flow. Let's say there is a pipe and this sphere is just subjected to a flow. Now I call this flow as an unbounded parabolic flow, because you can assume that there is a pipe that is here, but we will say that the influence of the walls of the pipe is not felt by the sphere, or in other words, the sphere is so small that you know the walls of the pipe will not have any influence on its velocity and the resulting disturbance velocity field. That's the idea behind using the word unbounded in this context. Okay, so as I said, this is an unbounded parabolic flow of some velocity profile u infinity, and because of the presence of this flow, the sphere moves with a velocity u, And since the axis of the flow and axis of the sphere are same, needless to say, the sphere will just move in the z direction, which is along its axis of symmetry, basically. Okay. So since the sphere will just move in the z direction, we just need to find out the magnitude of its velocity u in this context. Okay. And as I said, for evaluating this magnitude, we'll be using an additional constraint in this problem, which you did not use when you derived the Stokes drag, is that we'll be using the fact that the net hydrodynamic force on the sphere is equals to 0. This will give us an additional constraint, and from there we will evaluate this unknown velocity u, as we will see subsequently when we systematically solve this problem. And we will be using spherical coordinate system, but just to define the velocity field, I have used the cylindrical coordinate system here, because generally parabolic flows are more easily defined in cylindrical space, and then we'll convert this cylindrical system into the spherical system when we essentially solve this problem. But I denote my, just to denote the velocity field, I denote my cylindrical radius as rho, and this is z basically, which is the axis of symmetry, which means that with respect to an axis that is fixed to the particle center, I can write my flow as something like this. So this is just the concept of relative velocity that I have using. Since this is, there is an axis fixed with the particle center, and the particle itself is moving with u. So the flow with respect to this coordinate system, which is just, moving with the sphere, is just, 1 minus rho square, which is the nature of the parabolic flow, minus u, which is just the velocity of, which is the yet unknown velocity of the sphere that we will determine as a part of the solution of this problem. Okay. And the point is, so the idea is that we'll be solving for the flow field, meaning that we'll be ultimately, so what we need to do is ultimately we need to solve for the stream function. That's it. Because once the stream function is known, everything is known, the flow field, the drag, and everything. And later on we'll be seeing a theorem that is some that is kind of just, I would say, it's a shortcut to basically find out the net hydrodynamic drag on the sphere and the resulting velocity. But this is something that we will see later. And as I said, the objective is that we'll just evaluate the stream function. That's it. So for evaluating the stream function, there is a system of, there is a series of steps that we will follow, and we will highlight the steps one by one. Please bear with me on this so far if there is something new that you will just kind of get exposed to at this point of time. But everything will be understood when we systematically follow the steps in this problem. Okay. So the objective is that we will be solving for the stream function, and we know that the stream function satisfies E4 psi equal to 0. That means that we'll just need a solution for psi basically to solve this problem. Okay. But for that, I have written the velocity field u, and since we will be using we'll be solving this in spherical space. This is just the conversion of the spherical coordinate system into the Cartesian and the cylindrical is something that I have just written. For instance, I have a velocity field uz, which is nothing but this. This can be decomposed into u, r, and u theta, and we will see why we need to decompose them very shortly. And the cylindrical radius rho, which we denoted it here, that is the cylindrical radius, is related to the spherical radius r, as just rho is nothing but just r sine theta. You can just get it from here, because this is r, this is just r. So rho is just r times of the sine of the polar angle theta, basically. Okay. All right. So I hope you are with me on this so far. So the first step first is that the objective is to basically solve for the stream function. That's the idea. Okay, we need to solve for psi. And I know that in the creeping flow limit, in the creeping flow limit, my psi satisfies the biharmonic equation. Okay, and we know that in spherical space, as we just now saw, its E4 psi is basically equals to 0. Now, this, so there is something which is known as a method of eigenfunction expansion. I'll just write it here. So there is something which is known as the method of eigenfunction expansion. Okay, and using this method, what you basically do is you just write stream function. You just solve this by defining a vorticity, and then you use a stream function, and you use variable expansion only. That's it, because it's a PD. So you just use variable expansion to basically get a solution for psi. And this solution is so well known that for any axisymmetric bodies in which the flow is just taking place in the direction of axisymmetry of the body, the solution for psi for in the case of an axisymmetric problem is so well known that it it is just that this is solved, and its solution is basically known. That's the idea, and the manner in which it is solved is by using eigenfunction expansion, and we'll not use this because you have basically seen this. You have seen the glimpse of this. I think it was in cylindrical coordinate when you solve for the Stokes drag, but that's the same way through which it is done here in spherical space to reach the solution for psi. And since here we'll be solving for the we need to solve for other things also, I'll just say, and you just at this point you just take it for granted that you have solved this E for psi equal to 0, which is a PDE. You have solved this equation basically using this method of eigenfunction expansion, the idea of which you already got when you solve for the Stokes drag, into getting the form of the solution for psi as something like this. So its form is summation. So it's a series solution basically, where my n goes from 1 to infinity. It is an times r power n plus 3 plus bn times r power n plus 1 plus cn times 2 minus n. I think cn times r power 2 minus n plus dn times r power minus n. And then this is multiplied with something which is known as qn of eta. Okay, where these qn's, these are known as the Gegenbaer polynomial. These are known as Gegenbaer polynomials, and these are essentially obtained from the Legendre polynomials by using this relation. So Qn of eta is nothing but integral minus 1 to eta. It is Pn of eta d eta. Okay, it's just that if you know the Legendre polynomial, just use this integration to basically get the Gegenbaer polynomial. That's it. That's the idea basically. Okay, so I just repeat. So this form is so well known that the solution is well tabulated. That is for any axisymmetric body where the flow is taking place in the direction of in the direction of this axis of symmetry. The solution for psi, which satisfies the biharmonic equation, or in the creeping flow limit, in other words, is basically something like this. It's a series solution where there is a function of r. You can call this as some fn of r times qn of eta basically. That's where fn of r is this huge expansion in r that we will use. So as you can appreciate, the main crux of the problem is basically to calculate these constants an, bn, cns, and dn. Okay, and trust me that these ans and bns, we will see that this will be obtained from the knowledge of the far field flow, and the cns and dns is what essentially dictates the geometry of the object. For instance, it's a sphere in this case, and it will be obtained from the boundary condition that is applied on the surface of the geometry, which is a sphere. So in other words, this ans and bns is just a characteristic of the flow, while these cns and dns, these constants, are characteristics of the surface geometry. Okay, that's the idea. Okay, and all we need to do is to just evaluate these an, bn, cns, and dns. That's the idea. And for this we will follow a very systematic procedure, and I'll outline this now, that how do we basically get these constants an, bn, cns, and dns. But before that, let me quickly give you little bit idea on these Gegenbaer polynomials. For instance, I think Legendre, you guys know, you guys are aware with the Legendre polynomials. For instance, the Legendre polynomial satisfies the Legendre equation, and you know the Legendre equation. Okay, it's a second order, it's a second order homogeneous with a variable coefficient equation, and that's and the solution to the Legendre equation are the Legendre polynomials. For instance, that if my p1 of eta, that is the Legendre polynomial of the first kind, for n equal to 1 is, so that p1 of eta is just eta. Okay, or where eta is cos theta basically. Okay, so p1 of eta is just eta, that we just know, that is the first Legendre polynomial. Okay, of for n equal to 1. Then q1 of eta, you can just derive it by using the relation integral 1 to eta p1 of eta d eta. And since there is eta in the integration, we'll just do a change of, so we'll just use a dummy variable where we'll just call it as z, and then we'll integrate with respect to dz. And then this is just integral -1 to eta. P1 of z is just z, dz. And this becomes what? This becomes, so if you do this, it will just become half of eta square minus 1. I think that's it. It will be z square by 2, and this will become eta square minus 1. So if my p1 of eta, if my if the Legendre polynomial of the first kind is eta, then the Gegenberg polynomial of the first kind q1 of eta is just half of eta square minus 1. And then subsequently you can calculate this for, you know, n equal to 2, n equal to 3, and so long up to n equal to infinity. So for each Legendre, there exists the Gegenberg, which is defined by this relation. Basically, and that's the idea, you know, behind this Gegenberg polynomial. And this comes as an expansion when you basically use this eigenfunction expansion. Actually, there is a derivative of Legendre. It comes something like this, and not derivative, sorry, there is an integration of Legendre, very sorry, that comes basically like this. And in order to evaluate, you know, they have just named this integration over the Legendre as a separate, you know, polynomial function, which is just Gegenberg polynomials. That's the idea. There is nothing different than them. Okay. All right. So with this, let's get started into, you know, solving for these unknowns ans, bns, cns, and dns. Okay. So the first step is that I'll write it down, that the step 1 of the problem is to use the far field boundary condition to get an expression for the far field stream function. Okay, that's the first tip. So the idea is that since the far field velocity is known, because the knowledge of the far field velocity is provided to us as a part of the problem, we'll be using this knowledge of the far field velocity to basically get an expression of how the stream function would look like when r basically goes to infinity. That's the idea, and that's the first step that we will do. Okay, and let's do it. So what we have is, we have u infinity, which is nothing but the far field velocity, as just 1 minus of rho square minus u. Okay, Ez. This means that I know my uz, which is a z direction velocity at infinity. This is what? This is just 1 minus of rho square minus u. Now, since we are in spherical coordinate, first, in order to determine the stream function, we first need to, you know, transform this uz velocity into the velocity components in spherical coordinate space. And then what do we have? So for that, let's just use this, that I have my uz in this direction. So in spherical space, I will require this ur and u theta, because these are the only two velocities that I will have. I will not have u phi, because this is an axisymmetric problem. So I just need to basically, you know, calculate this unknown ur and this u theta from the given uz velocity field at r tending to infinity. Okay, so so if I know uz, then my ur is just uz cos theta. That's just from the geometry, because this is theta. If this is theta, and then if these two are parallel, then this angle is also theta. So ur is just uz cos theta, and similarly my u theta is going to be minus of uz sine theta, meaning because of the fact that I consider my u theta in this direction basically, and uz sine theta would be in this direction, so u theta is basically equal to minus of uz sine theta. So that's the idea that we will follow. Okay, so so this means that that's all we'll do. So the far field, I'll write it down, the far field velocity in spherical coordinates, that is my ur infinity and u theta infinity, are something like this. So my ur infinity is just going to be my uz infinity times cos of theta, and in terms of eta, because we are in the eta variable, it is just uz times eta basically, because remember eta is just cos theta, that's it. And I'll write it down that my eta is just cos theta. Okay, and this means that my ur infinity, see, the objective is to get the stream function, and for stream function I need two velocity components, and here the two velocity components are ur and u theta, because the problem is axisymmetric, and that's the reason why we are transforming the uz into ur and u theta. That's it. So this ur infinity is now uz infinity, and I know uz infinity is basically this 1 minus of rho square minus u square. This is 1 minus of rho square minus u, not u square, just u. And then I have eta. And remember, I also need to write rho in cylindrical in spherical space. This is the cylindrical radius. So rho is nothing but r sine theta. And sine theta is just nothing but 1 minus of eta square. So that's rho basically. Which means that my ur is nothing but 1 minus of r square times 1 minus eta square minus u, and then there is a multiplication with eta. Okay. All right. Similarly, I can also write my u theta, that is for ur. The objective is to find u infinity. You can either use ur and u theta as the stream function velocity relation to basically get u infinity, but we'll also write it down for u infinity first. Okay, u theta infinity first. So u theta infinity, as I said, it was nothing but minus of uz infinity times sine theta. Okay, and I know that, you know, this uz infinity and sine theta is just 1 minus of eta square. Okay, which means u theta infinity is equal to minus of uz infinity is what? Uz infinity is this 1 minus of rho square minus u basically. So it is minus of 1 minus of rho square minus u times square root of 1 minus eta square. Okay, and I know that rho is nothing but r times of square root of 1 minus eta square. So this u theta infinity becomes minus of 1 minus of r square 1 minus eta square minus u times square root of 1 minus eta square. Where recall that this u is the unknown velocity of the sphere that we will basically calculate. Okay, so this is yet an unknown which we will specify later on. So this will do at the last part of the problem to, you know, get the velocity of the sphere. Okay. All right. So now this is how the velocity fields look like. Okay, so we'll name this equation. So this E for psi equal to 0, this is the first equation we'll name. Its solution, we'll name it as 1a. Okay, and then, you know, this is the velocity profile, and then, you know, these are the velocity components, these are the far field velocity components. We'll name it as 2a and 2b. All right, see, the objective now is to calculate the far field stream function. Okay, and we'll be using the far field velocity to basically calculate the far field stream function. And for that, either you can use the definition of ur infinity, or you can use the definition of u theta infinity in order to get psi infinity basically. But I will use u theta infinity to basically you know, calculate psi infinity. That's for the ease of computation, and we will see computation means that the use, that's for the ease of calculation, and we will see that why, you know, basically using u theta infinity, you know, decreases the number of steps in the problem. So I know that the relationship between my velocity field and a stream function in spherical space is something like this. So u theta infinity is 1 by square root of 1 minus eta square, which is nothing but sine theta, times 1 upon r times del psi infinity by del r. Just how steam, you know, my u direction velocity field is del psi by del y. This is how the velocity field and the stream functions are related in spherical coordinate system. That's the idea. Okay, so you can get this relation from any standard book or on how the velocity field and the stream function is related in spherical space. Okay, now the objective is to calculate psi infinity. So we'll be, you know, substituting the value of u theta infinity from here. So it just becomes that minus of 1 by square root of 1 minus eta square, okay, times 1 upon r del psi infinity by del r, and this is equal to this term. Okay, I'll just name this as 3, the relationship between u theta and psi. And then this becomes what? This becomes minus of 1 minus r square into 1 minus eta squared, okay, minus u, and then there is square root of 1 minus eta squared. Okay, so if I just do some simplification, then this minus and minus sign cancels. This I will take it to this term, which this term will just become 1 minus eta square, and the r I'll just keep it, I'll multiply this r into this bracket. That's what I will do. So this means that I just get del psi by del r as what? As r minus r cube, okay, into 1 minus eta squared, okay, times 1 minus eta squared. That's it. Okay, so this is how my del psi infinity by del r look like. So in order to calculate psi infinity, all I just need to do is integrate this with respect to r. That's what we will do. So integrate with respect to r, and if we do this, I'll just get psi infinity, which will be a function of r and eta, as r square minus r power 4. Okay, this will become r square by 2 because this is r, so it will just become r square by 2 minus r power 4 by 4, okay, times of 1 minus of eta squared, and then there is this 1 minus eta square which is here, okay, plus remember since psi infinity is a function of both r and eta, and I'm just integrating with respect to r, so I'll get a constant which will be named as, let's say, a tilde of eta into this. But the good thing is, since we are looking for far field, that is, since we are looking at a condition where my r tends to infinity, this means that these terms, that is r square and r power 4, this term will be much greater than a tilde of eta, because a tilde of eta is what? It is just a function of cos and sine. So this will be an order 1 quantity. So an order 1 quantity with respect to terms where this r basically goes to infinity, meaning that in the limit, so what I'm trying to say is that in the limit, in the limit r tending to infinity, my my a tilde by a tilde of eta by this term, which is r square by 2 minus r power 4 by 4 into 1 minus of eta squared, times, there is this 1 minus of eta squared. This will basically, go to 0 because of the fact that this a tilde of eta is an order 1 quantity, and this is just this is very much larger than order 1. This quantity, is very much larger than order 1 because of the fact that I'm looking for the far field solution, meaning that my r basically goes to infinity, which just means that this a tilde is basically equal to 0 as r tending to infinity. So that's the reason why I use the u theta component of velocity to get the expression for psi infinity, and not the ur component of velocity. This is just an easy way of looking into calculating psi infinity. Okay, so this means that the psi infinity that we get is something like this. So it is, so the psi infinity that we get, which is of course a function of r and eta, as what it is. Okay. I think I forgot to write one more term. There is an u here, remember, right? So there will be an u that is present. So I think there will be a minus of u here. Yes, I think so. Yeah, so there will be a u here, which is just minus of u r, and then this will be 1 minus u. Okay, I just forgot to write this. There will be a 1 minus u here. If I just take common, if I just take r common, I'll just get 1 minus of u, and then there will be just this 1 minus of u basically. Okay, anyways, so that's the psi infinity. So psi infinity is just so then psi infinity is what? It is just r square by 2 times 1 minus u, okay, minus r power 4 by 4 into 1 minus of eta squared, okay, and then there is also this 1 minus of eta square outside. So if I break, this, if I just bring this 1 minus of eta square inside, my expression for psi infinity, this psi infinity as a function of r and eta, this would look like what? It would look like r square by 2 into 1 minus of u into 1 minus eta squared, okay, minus r power 4 by 4 into 1 minus of eta squared whole square. Okay, all right. Okay, so now what we will do is I will just write this, expression for u as an increasing, polynomial for eta, meaning that I will write the coefficient of eta power 0, eta power 1 if there are, eta power 2, and so on up to, eta power 4, basically. So I'll just rearrange these terms and write this expansion in an increasing, polynomial of eta, and we will see very shortly why we need to basically do this, okay? So if I do that, if I just write this, so rearranging, and I'll just skip the algebra here because this is already done in my end. So it's just that, so the idea is just I'll just break these, terms and write these terms as polynomial functions of eta power 0 plus eta square and eta power 4. These are the terms that we'll basically have, okay? So rearranging and writing, what we will get is we'll get psi infinity as a function of r and eta as something like this. So it will be 1 minus u times r square by 2 minus r square r to the power 4 by 4, and then I'll have this eta power 0 which is just 1, and then I'll have plus r square by 2 minus 1 minus of u, okay, into r square by 2, and this would be r square by 4, okay, so it's going to be r square by 4, okay, and then I'll have an eta square here, and then this is r power 4 by 4 into eta power 4, okay. So it's just nothing, we are just rearranging these terms over here to write this as a polynomial function of eta power 0, eta square, and eta power 4, and we'll see very shortly why we are basically, trying to get into these kind of form, okay. It's just the rearrangement that we are doing, and it's nothing else. If you just combine these terms, if you just combine these terms, you will basically get these terms only, that's it. Okay, so this is the final form, okay, this is the final form for psi that that we will uh, that we will use. So this is the final form for psi infinity that we seek to in the uh, in the first place. So the objective, remember, of the first step was to get the psi infinity, and this is what psi infinity basically looks like for us, okay. Now the second step, I hope it is clear. I'll stop here for a couple of minutes. I'll just go and fill my mug with some water. I'll just come in 1 minute. Okay. Sorry for the interruption. So, so that's the psi infinity that we get from the knowledge of the, far field background flow. Okay. Where again I say that this u, that is the velocity of the sphere, is an unknown of the, or a velocity of the spherical particle. It's an unknown, and we will find this later as a part of our solution. So let's not worry about this. But this is how, apart from this u, this is how, my psi infinity looks like. So this is how my stream function looks like at far field basically. Okay. So the next step, that is the step 2. So I think we have written this as step 1. Okay, the step 1 is to use the far field boundary condition to get an expression for the far field stream function. That is something that we did. Okay, the step 2 is, I'll write it down. So the step 2 is basically extract the possible modes of, okay, I'll write it as extract the possible modes for the solution of psi, for the solution of psi from the far field stream function. Okay, so what I'm trying to say is that I'll explain to you here. Okay, what I'm trying to do. So the idea is something like this. Okay, I'll write it down here and I'll do it in the next step, in the next space. So let's try to understand what we mean by extracting the possible modes for the solution of psi from the far field stream function. Okay, so so what we are doing is basically we are solving. So there is a sphere. Okay, there is a sphere, and this sphere is subjected to, the sphere is subjected to some, some background flow. For instance, this can be any background flow, but here we have a, we have a parabolic flow, let's say, of some form. Okay, let's say we have a parabolic flow here. That's the question that we are solving for. Okay, so what I'm trying to say is that when, let's say my r basically goes to infinity. Okay, when my r, goes to infinity, what I do know is that at a particular r, at a particular r, and in this case when my r basically goes to infinity, I know the form of the stream function psi infinity. Okay, this psi infinity is basically known. Okay, so which is basically this is something that we have derived. And how do we know this? This is known from the knowledge of the velocity field that we already have. So the idea is that just like in Fourier series, if we have a known function, you can always decompose this into a bunch of sine and cosine forms, into a sine and cosines basically. And for instance, if let's say, so just from the, so from the knowledge of Fourier series, what I do is, let's say I have a function x. Okay, I can always decompose this function as a bunch of sine and cosine, which is something like this. Okay, so it is, so you know that in Cartesian space it is a0 plus summation n equal to 1 to infinity some a n cos, cos n pi x by L plus, sine, or let's not do it in general. Let's say it is just cos, this just, let's say, some cos nx plus some bn sin nx, and then this expansion is, this is valid for, any x between -1 to 1. Okay, because this is the region where the cos and sin are orthogonal actually. So the idea is, in a domain which is from -1 to 1, I can represent any function which can be of any arbitrary shape. It's not necessary that this function has to be continuous. It can be a discrete function as well. But in the domain from -1 to 1, I can represent any function as, an orthogonal, as a bunch, as a summations, as a sum of basically some cos functions, as a sum of some orthogonal functions which are cos and sine if we are sticking into a Cartesian space basically. So any functions in the domain X going from -1 to 1, I can represent this as a bunch of sine and cos functions. Okay, that's the idea in basically this Cartesian space. Similarly, in case of spherical space, in case of spherical coordinate system, I can represent any function which is known at let's say at a given at a given radius. For instance, this r is fixed. I can represent any function which is basically, so this function is basically varying. How it is basically varying, if you can see, it is varying from eta, which is my cos. So these functions are basically varying from eta equal to -1 to 1. So in this domain, just like in sine and cos, in spherical space, if I want to represent any function which is a function of eta, okay, because I have fixed my r, it is just a function of eta which is vary from -1 to r as a bunch of orthogonal functions. These orthogonal functions, instead of it being sine and cos in Cartesian coordinate, it becomes Gegenwehr. So the idea is I am representing any random function which is known. Let's say this be any random function that I am defining on this circle, which is at r equal to infinity. This random function can can be written as I can always write this random function as, let's say, how do I write? Let's say this function is some mu of, let's say, eta. I can write this as summation of n equal to 1 to infinity, some, let's say lambda, let's say this is some lambda n times gn of eta. Okay, it's the same logic that I have used for sine and cos, but I cannot use sine and cos here because it's a spherical space basically. Now this mu of eta, this is known to us, right? Because this function is known to us. Okay, so all I need to do is, since this is known, I need to know which modes of Gegenwehr are basically present in the far field condition of psi. And then if this is known, that's all. That means I know that what modes are basically present in the solution of the string function at psi infinity. And that's the reason why I am representing psi infinity as as a series expansion of eta power 0 and eta square and eta power 4. Basically what you need to do is, you just need to extract these lambda n's. That's it. That's all that you need to do for getting the modes of, you just need to see that which values of n are present in the known function mu of eta. Basically, that's the idea. Okay, I'll stop here for a couple of minutes. I like you guys to basically understand what I say here, what I said here, and then we will proceed with finding the modes of the solution for psi from the stream function basically. So the idea is that if for a particular r, if for a particular r, I know that these many modes are present, then for any generic r, then for any generic r, I can similarly use the same analogy to write my to write my solution, but this time it will just be lambda n of r times gn of eta. It is just that difference. Okay, where I know that when r tending to infinity, my lambda n of r basically becomes my lambda n infinity, which is just this, this form. So that's the idea. So the modes, you can appreciate the modes, that is the values of n that are present in the far field condition will dictate its values for any arbitrary r. Is just that the coefficients will just be a function of r, but the modes will be there. That comes from the form from that we get when we define the far field stream function. I hope you kind of understand what I'm trying to say here. So that's the reason why we use the far field condition to basically get the modes that are present in the solution from psi. And this is all possible because just like sine and cos, these Gegenwehrs are also orthogonal functions in the limit, of course, when eta goes from -1 to 1. And that's the limit that we are looking in this problem basically. Okay, so the idea is that we will basically try to extract the modes of Gegenwehr that are present here. Okay, so I will now represent, in order to do this extraction, there is a well defined rule which is known as orthogonality principle. uh, you can either use the orthogonality principle just like of sine and cos. There is an orthogonality principle for Gegenbaer as well. You can use the orthogonality principle for Gegenbaer to basically extract the modes. But the good thing is that since we have already written this as a series expansion of for eta 0 and eta 2 and eta power 4, we can just do mere comparison to basically get the mode, basically get the mode. That is typically because the form of the solution is an algebraic form, and in principle, we are just using orthogonality relations only. That's the thing. Okay. So what I will now do is I will just represent. I will just say that okay, my psi infinity as a function of eta, and of course, and some function of it. So psi infinity is a function of eta and r. So this psi infinity, I will say that it is of this form. It is some. It is, let's say, of okay. It is of the form, let's say, summation n equal to 1 to infinity some fn of r, okay, where r is at infinity, remember, times qn of eta. It's just that I am right, it's the same thing, I am writing a known function as a series solution of some orthogonal functions, and the idea is that I'll try to extract these modes here from the known value of psi infinity, which I already have in this problem basically. So this means if I expand this summation, I can write this down as some, let's say, what I can write this down as some f1 of r q1 of eta, okay, plus f2 of r q2 of eta plus f3 of r, let's say q3 of eta, plus all other terms. Let's say I'll have f4 of r, q4 of eta, and so long and so forth. Okay, then what you need to do is you just need to use the orthogonality relations of this Gegenbaer, or you just need to use the orthogonality relations of q1, q2, q3, that is this Gegenbaer polynomial, to basically get this constant f1, f2, f3, and f4. Okay, that's all you need to do. I'll skip this step as of now. You can just look into any standard book of orthogonality relations, and then you should be in a position of basically getting into this f1, this basically getting into this constant f1, f2, f3, and f4, because this becomes a tedious maths at this point of time. But I will ask you guys to do it yourself. It is just how you calculate the constants an, a0, and bn's by using the orthogonality relation of cos and sine in Fourier series. That's it. That's the same thing that you need to do. Okay, so I'll just write it down here using the orthogonality relation, orthogonality relations. What I get is the far field stream function have the following modes. Okay, it have the following form basically. So psi infinity can be, so it just has the n equal to 1 and 3 mode that you can basically verify by using the orthogonality relation, because the form of the stream function at psi infinity is already known. That's the thing. Or what you can do is you can do one more thing, that's an easier thing. Just write this, expand these q1s, q2, and q3s in their functional form, and then just compare this with basically this. That's another way of getting the values of these f1s and f2s and f3s basically. Okay, so the idea is that you will see that if you use the orthogonality, what you will see is you will see that only you will only see that n equal to 1 and n equal to 3 modes survive, and the rest the okay, it's just not necessary to write. So for all the n modes, so for all these summations that I wrote, only n equal to 1 and n equal to 3 mode that survives based on the known form of the stream function that we basically have. Okay, then this means that my psi infinity is just of the form some f1 of r times q1 of eta plus f3 of r times q3 of eta, where this f1 and f3 are of the following form. So it just becomes, so this psi infinity just becomes 2 by 5. So this f1s and f3 are of the following form. So f1 is of the form 2 by 5 r power 4 minus 1 minus u times r squared. Okay, and then this is q1 of eta. Okay, and then this is minus for third mode, it is just minus 2 by 5 r power 4 q3 of eta. Basically, it's something like this, where this is f1. This bunch is basically your f1, and this bunch 2 by 5 r power 4 with a minus, this is your f3 of r. Okay, that's it. This you get by using the orthogonality principle. So yeah, so this means that in the series solution only two modes survive, n equal to 1 and n equal to 3. And remember, in the Stokes first problem, if you paid a closer look, you will see that only n equal to 1 move survived, because of the fact that it's a non-linear background flow. It's a non-linear background flow. That's the reason why we have the second mode, which is n equal to 3, and rest all other modes are 0. And you can easily verify it just by using the orthogonality conditions of this Gegenwert polynomials. Okay. All right. So this is the psi infinity that we get. So now, as I said, just come back to here. So since I know that the form of the psi infinity, the form that I use here, I only have n equal to 1 and n equal to 3 modes in the far field flow. This means that for any generic radius r, I will still have n equal to 1 and n equal to 3 mode only, because of the fact that the Gegenwert polynomials are orthogonal. It's just that I need to find out these unknowns lambda n of r. That's it. The number of modes will be dictated, as I said, this will be dictated by the far field flow. It is just that I need to evaluate the extras, evaluate the extra constant that comes because of the fact that now I am at a finite radius. And remember, when I take this limit r tending to infinity lambda n of r, that is when I take this limit, it should always approach this value, basically lambda n infinity. Okay, but I hope you appreciate that the modes that are present at any generic location r, that is the solution for psi, that will be the same that we get when it is at far field, basically. And this is because just like sine and cos, as I have said repeatedly, the Gegenwert polynomials, these are also orthogonal in nature, basically. Okay, so this means that in the solution so I'll write it down, that in the solution of psi, which was something like this. So psi is r. So psi as a function of r and eta. So remember, the solution was what? The solution was something like this. It is this solution, right? It is basically this solution. So in this solution, I just have n equal to 1 and n equal to 3 modes, basically. That's it. So I'll just write this form of the solution once again, just for you to be clear. So remember, this solution was what? So psi was summation n equal to 1 to infinity a n times r is just r power n plus 3 plus b n times r power n plus 1 plus c n times r power 2 minus n plus d n times r power minus n, and then this is q n of eta. And I know that, and what do I know? I know that only n equal to 1 and 3 modes survive, which means now I can write this psi as what? As a function of r and eta as summation. So it will just be for n equal to 1 and 3. So it will just becomes what? A1 times r power 4 plus b1 times r power r square plus c1 times r plus d1 times r power minus 1, and then this would be qn of eta. Okay, plus for n equal to 3, I'll have a3 times r power 6 plus b3 times r power 4. I think that's it, right? b3 times r power 4 plus c3 times r power, so I'm writing this for n equal to 3, so this becomes r power minus 1 plus d3 times r power minus 3. Okay, and this is for q3 of eta. Okay, and This is for Q1. So now what I can do is I can segregate this as something like this. So I can write it, I can bring all the A's and B's together because this will carry the signature of the far field. And then I can just write it as A1 times R power 4 plus B1 R square Q1 of eta plus A3 R power 6 plus B3 R power 4 times, Q3 plus I can then write this the other terms as C1R plus D1 times R power minus 1, okay, plus C3 times R power minus 1 plus D3 times R power minus 3, okay, and this would be multiplied with Q1 and this would be multiplied with Q3. The reason why I am doing is that you can now just compare this term, you can compare this term with psi infinity because of the fact that this, at r tending to infinity, this we will only get this contribution, and this can be obtained from the form of psi infinity that we already have. For instance, if you just compare this term with the form of psi infinity, you can easily show that your a1 is 2 by 5. You can easily show that just by comparison. You can show that your a1 just comes out to be 2 by 5. Why? Because we know that my for psi infinity for the 1th mode is just 2 by 5 r power 4, and I have r power 4 only on this term. So this means that a1 here would just come out to be equal to 2 by 5. And you can also show that your a3 is basically equal to 0 because you don't have an r power 6 term in your form of psi infinity basically. And similarly, you can show that your b1 comes out to be equal to u minus 1, and b3 basically comes out to be equal to minus 2 by 5 uh, minus 2 by 5, which means you can now, nicely write your psi, the solution for psi, which is a function of r and eta, as the psi infinity, which is of course again a function of r and eta plus psi disturbance, where the psi disturbance is just governed by this term basically. You can say that your psi disturbance now, you can say that your psi disturbance, your psi d, that is your psi disturbance, is nothing but summation n equal to 1 to infinity. It will just contain the c's term. It will just be cn times r power 2 minus n plus dn times r power minus n times qn plus psi infinity basically. And psi infinity is just this term. You know the form of psi infinity because we all we just have derived this. Okay, this is the form of psi infinity. So what you are doing is you are essentially writing the stream function as a contribution from just the far field flow only, which is just be at a signature of the far field flow, which is known to us, which is basically known to us, and then a disturbance term which comes because of the object. For instance, we have a sphere, and we know that here we'll just have n equal to n equal to 1 and 3 modes only basically. Okay, so that's the idea so all that is remaining is to basically evaluate. So the next step is just to evaluate C1, D1, C3, D3 from the boundary conditions on the surface of the sphere. That's it. From the sphere. From the surface of the sphere. Surface of the sphere. Okay. That's all that you need to do. And then we'll be using something which is known as a hydrodynamic force free condition to basically, come up with a solution of this form. So we'll stop here. We'll stop here today, and we'll proceed it from the so the step for calculating this C1, D1, C3, and D3, and we will see that just by knowing C1 is enough to give us the velocity u, and we'll use a theorem for that to basically look into this. But anyways, this will be doing it in the next class. But the objective is that you just now need to use the boundary condition on the surface of the sphere basically to calculate these C1s, D1s, C3s, and D3s. Okay, and that is sufficient to give you the form of stream function. So I hope you realize that how powerful is orthogonality is, because it just says that any known function, you can always write this as a sum of some orthogonal functions, okay? And these orthogonal functions happen to be sine and cos if you are in Cartesian space. This happens to be Gegenwehr if you are in spherical space, okay? And if you are in cylindrical space, you can show that these orthogonal functions happens to be Legendre, I guess. Yeah, in cylindrical space it happens to be Legendre, okay? So that's the idea behind this, okay? So I hope you are clear. This is a little bit involved topic, but I hope you are clear on this. And I hope you appreciated the math behind, how did we get the modes, the number of modes that are present from the solution, from the far field solution of stream function, okay? Just as a quick recap, we know that basically we need to solve for this biharmonic equation of psi, and I said that the solution of this psi is known to us. It's just that we need to extract the modes that are present here. And for this, what we do is we use the knowledge of the far field velocity to get the expression for the far field stream function, which is something like this. And then I say that any function, okay, any function uh, that is so it's just that at any radius, let's say at radius r tending to infinity, I can write any function which is varying from -1 to 1 as a series solution of some orthogonal functions which happen to be Gegenwehr here. And just that from this knowledge, I just need to use the orthogonality principle to extract the number of modes that are basically present in this functional form of psi. And that's what we did, and we saw that in this problem only n equal to 1 and 3 modes survive, although explicitly I did not show the steps behind this orthogonality relation, but I would encourage you to basically do this at your end and try to appreciate that, okay, there is only these 3 modes that basically survive in this analysis. And once we know, we can now write psi as a psi infinity which is known plus a psi disturbance, and this psi disturbance is carried in this in through these constants cns and dns, which we will find out by using the boundary conditions on the surface of the object basically. So the shape of the object is reflected in this psi disturbance only, okay? It's not reflected in psi infinity. And psi infinity is just the signature of the flow itself. It's just the signature of the background flow. And psi infinity is important because it gives the modes that are present in the solution for psi basically. Okay. And again, this is a hallmark of creeping flow analysis, and also the principle of orthogonality that we use. Okay. And all these things that you can do because your governing equations is linear, because your equation that governs psi is just del 4 psi is equal to 0, or it is just e4 psi equals to 0. That's it. Okay, so I'll stop here for today. In the next class, we'll just see how do we apply the boundary condition on the sphere to basically get this constant, and then the unknown velocity u, which we still need to evaluate as a part of our solution. Once that is done, we'll stop the analysis of creeping flows, and then we'll move to boundary layer in the next class. Boundary layer analysis in the next class. I hope this is fine with everyone. Okay, I'll stop here for a couple of minutes. If there are any questions, we will take it up. And please, keep posting your questions in the discussion forum, and we'll try to answer that as and when we find a suitable answer to your question. Okay. And I thank everyone for listening to these videos, and please let me know if there are any doubts associated with this, and I'll be happy to clarify them once you post your doubt. Okay. Okay. All right then. Thank you very much, guys. We'll meet in the next week at at the same time using the same link. Thank you very much.